Okay, so this is the first video of Chapter 8, and Chapter 8 is on chemical bonding and Lewis structures. It seems a little dumb that we're 8 chapters into a semester and we just now for the first time mentioned chemical bonds, but that's okay. We'll get through it. We'll figure it out. Okay, so in terms of chemical bonding, there are two main types. One we've kind of seen like a million times, and I'm going to mention it real fast, which is ionic bonding, or ionic bonds. Essentially, this is when you have a cation and an anion. Okay, so for example, you have like sodium and chlorine. Sodium has one more electron than a noble gas and would really like to get rid of one electron. Chlorine has one electron shy of being a noble gas and would really like to steal one. So sodium gives up an electron. Okay. I don't care if you draw this. We'll probably never have to draw this ever. But if you ever get to organic chemistry, a double-pointed arrow means 2 electrons being transferred. A single-sided arrow means 1 electron. I don't know. It'll be important next year if you take organic chemistry. But the result is that you get sodium has a plus charge, chlorine has a minus charge, and basically positive is attracted to negative, and there's what's called an electrostatic interaction. Positive is attracted to negative. It's literally just like magnets. Okay, we have been dealing with this type of stuff since like chapter 2, chapter 3, yeah, chapter 2 probably. We're done with that. We're not going to talk about that one right now. Okay, what we care about are covalent bonds. We haven't really done much with this, so we need to talk about this idea. Covalent bonds are the idea of bonds being formed by sharing pairs of electrons. Pairs of electrons. Okay, so the idea is it's not about things forming charges, it's about things sharing electrons and both of them being more stable because of it. Okay, so how we decide whether or not things are going to form bond is based on something called the octet rule. The octet rule is not a perfect name for this, but it's what everybody uses, so we're going to keep using it. Okay. Covalent bonds is pretty much what the entire friggin' chapter is about. Okay, so the octet rule. This is the idea, we kind of in class mentioned the idea of valence electrons. The idea is that atoms will, well, get rid of, beg, borrow, or steal electrons. Basically, they'll give up electrons or steal electrons from somebody else, or they'll share electrons until the atoms in the molecules have 8 valence electrons. So atoms will gain, lose, or share electrons until they get 8 valence electrons. And the reason that 8 is a magic number here, the reason 8 is important, is if you have a full s orbital and a full p orbital, that's the same as a noble gas. And since we said the d block, if it gets full, counts as core electrons, it would still be 2 plus 6. So to be like any of the noble gases, essentially you want 8. Even if you lose some, like potassium has, you know, you could visualize 3s2, 3p6 would be like the 8. It almost has like 9, so losing 1 would give it its 8. Essentially, it's another way of phrasing that it wants to be like a noble gas. Okay. The exception to this is not actually in the D block this time. It's actually hydrogen. Hydrogen only needs 2 electrons to be considered to have an octet, which is why the term octet is not appropriate for everything. But literally every element on the periodic table, except for hydrogen, will try to shoot for 8 valence electrons. Okay. So let's kind of get like the overview of what this looks like before we get into the gory details here. Okay, when electrons are shared, so continuing this down here, I guess, This is all based on the octet rule. Anytime you have a single bond, which is just represented by a single line, this is made from 2 electrons. Okay. Anytime you have a double bond, this is made from 4 electrons. And anytime you have a triple bond, that is equal to 6 electrons. You cannot have a quadruple bond. We'll address why that is in the next chapter because it has to do with like the 3-dimensional geometry of the molecules. Okay. Has to do with the shape of p orbitals actually. So, single bond, double bond, triple bond, these are all really, really common. I know I wrote equal signs after these lines that represent bonds. Sorry, it's not perfect. Okay. So for example, if you had something like hydrogen, hydrogen only needs 2 electrons to be happy. So, hydrogen, you know, if it has 1 electron, which is what we'd expect for a typical hydrogen, its element 1 has 1 electron. And you had another hydrogen, and it also has 1 electron. You have a couple of options. One possible, because they both want 2. One option is that this hydrogen could steal an electron and it would have 2, but then this one would have 0. This one could steal an electron and this one would have 2, and this one would have 0. Or what happens most of the time, when things form covalent bonds, what happens is they share the electrons. And so we could draw it kind of like this. Okay, these are 2 shared electrons. Okay, we don't typically write it like that. We use the bonding system. So we would typically write it like that. But the idea is this hydrogen has access to 2 electrons, and this hydrogen has access to 2 electrons. So by sharing them, making a covalent bond, they both have access to 2 electrons, so they've got their octet, for lack of a better word. This works for bigger elements as well. Okay. I kind of jumped the gun here. I need to explain where these little dot things come from, okay, before we go too much farther here. So, Lewis structures is one of our goals in this thing. A guy named Lewis, who liked to put his name all over everything in chemistry, came up with lots of stuff, honestly. He's responsible for the most common way to draw molecules in 2 dimensions. He also has an entire category of acids and bases named after him based off the definition that he came up with. He also came up with what are called Lewis dot symbols. Most of the stuff that this guy has done is pretty genius. I could have come up with this. It's not that hard. Okay, so essentially what we do is we use the elemental symbol, sorry, couldn't write for a second, elemental symbol and dots to represent the octet rule. So, how do we keep track of this? Okay, it basically it's based on valence electrons. I know I mentioned in class how valence electrons work, but I'm going to shortcut the whole thing. This whole covalent bond thing mostly only applies to nonmetals, so we can pretty much ignore all of this stuff. These things almost always form charges if they're going to form compounds. And honestly, these numbers at the top tell you how many valence electrons any of these have. So oxygen is in column 6A, it has 6. Carbon is in column 4A, it has 4. Chlorine is in 7A, it has 7. That's literally the entire concept. So you don't even have to do orbital diagrams and electron configurations to figure out valence electrons. So, if you had something like carbon, okay, the way we're going to do this is we are going to visualize there being like a square around this. You don't actually ever draw the square, but we're visualizing there being 4 sides. So I'm just going to kind of loosely draw a square. Not a very good one anyway. And the idea is this almost feels like like orbital diagrams with how we had to, if we were putting arrows into boxes, we had to give each one up arrow before any of them got 2. So this is in column 4A, so it has 4 valence electrons. And what we're going to do is we're going to put a dot on each side until we hit the number we're shooting for. So for carbon, we're shooting for 4. So carbon has 4 dots, so this is what it would look like. This is how we would typically write it. Getting rid of the box now. But you visualize there being 4 sides, and each side gets 1 dot before any gets 2. So this should feel somewhat familiar. If you have something like oxygen, so I guess I'll put 4 valence electrons. If you had something like oxygen, this has 6 valence electrons. Okay? And so it has 6 because it's in column 6A. Okay. So essentially, you start out with 1, 2, 3, 4. Okay. When I was in high school, my high school teacher, when he was teaching us this, he said, okay, now when it comes time to pair them, you make sure you start at the top and then you go to opposite sides. I will tell you that it really, 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 really does not matter at all. Just put them wherever you want. Okay, so we have 4 valence electrons. We need to put 2 more in, so we start pairing them. I'm going to pair them here and here because I randomly chose those 2. Okay. If you had something like neon, this has 8 valence electrons. So this would be meeting the octet rule. It would have all 8. So 1, 2, 3, 4, 5, 6, 7, 8. And this is what it would look like if it had a full octet. Okay, so it's just a way of visualizing the octet rule. It's really not that complicated. It's actually really, really easy. So if we looked at, I kind of jumped the gun here and I'd started that with hydrogen. Hydrogen has 1 dot and then we paired them up. Okay. If we did that with something more complicated, like chlorine. Chlorine is diatomic. Okay. So we could visualize 2 chlorines and we could put our dots on there. Chlorine is in column 7A, so it should have 7 dots, 7 valence electrons. I am intentionally going to do them like this. I have a reason for doing it this time. Okay, there's 4, 5, 6, 7. And on this one we have 1, 2, 3, 4, 5, 6, 7. Okay, so we can see visually that this is the ideal answer, to have all sides having 2. This one has 7, and this one has 7. So by sharing these unpaired electrons in the middle, we can make this thing happy. Okay, so when you're doing Lewis structures, I guess it's Lewis dot symbols, but when we do Lewis structures, the dots are important. They do represent pairs of electrons that are important. Okay. The lines that we use represent bonding pairs of electrons. So each line represents 2 electrons, which is why they're pairs. These are non-bonding pairs, usually called lone pairs. Bonding pairs they count towards the total number of electrons for each of the atoms connected to it. These ones only count towards the 1 atom that they're connected to. So this chlorine has 2, 4, 6, and then this bond counts as 2 more, so that's 8. This chlorine has 2, 4, 6, 8. So they both have their octet, they're happy. This is why chlorine is diatomic. Okay. If we try this for something like nitrogen, nitrogen is also diatomic. Okay. Nitrogen is in column 5A. Okay, so that would be 5 valence electrons. We have 2 of them. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. We'll do it like that. Okay. So they both want 8, and they both only have 5 right now. If we share these, that gives us 2, 4, 5, 6. So that's not enough. And they both want more, so do another one. 2, 4, 6, 7. This would give it 2, 4, 6, 8, and this would have 2, 4, 6, 8. So they both have 8. But nitrogen is also diatomic, but it doesn't look the same as this one. It ends up forming a triple bond. And it still has a lone pair on each side. So in terms of counting this nitrogen has 2, 4, 6, 8, and this nitrogen has 2, 4, 6, 8. The bonds count towards both of them. Okay? So the idea is, this is kind of what Lewis structures are about, and what Lewis dot symbols are about, is representing this octet rule, the reason that it's going to form bonds and share things. Okay, So I'm gonna generalize something really fast, and then we'll call this video over. So there are exceptions to what I'm about to write down, and we're gonna have to go through the gory details in the next video. Okay, but in general, carbon forms 4 bonds. They can be in the form of single bonds, double bonds, triple bonds, whatever, but there's usually a total of 4 sticks and no lone pairs. In general, hydrogen can, well, there's no exceptions to this. Hydrogen can only form 1 bond. It will never, ever, 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 ever have lone pairs on it. No dots, ever. Okay. Nitrogen typically has 3 bonds and a lone pair. These can be in the form of like a double bond and a single bond, or a triple bond and a lone pair, whatever. Okay, but there's 3 sticks and 2 dots. Okay. Oxygen likes to form 2 bonds and 2 lone pairs. Okay. The halogens, which for some reason somebody decided that they should be abbreviated as an X. I don't know who thought this was a good idea, but so this would be fluorine, chlorine, bromine, iodine, astatine, I guess technically might follow this, but it's radioactive, we ignore it. So it likes to form 1 bond and 3 lone pairs. You'll notice that for any of these, it forms 2, 4, 6, 8. Hydrogen's happy with 2, it's the one exception to this. Nitrogen's got 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8. This is the ideal form of them hitting their octet rule. There are definitely times when they can't do this, but if you ever have to make a decision and you're like, I wonder where I should put these lone pairs and stuff, this would be the ideal situation. Okay, doesn't mean it always happens, but it's the best case scenario. Okay, we'll stop there.